Hi, my name is Bill Kinney. This is part one of a series I'm making on comparing linear and exponential functions. You might say comparing and contrasting, but that was a little longer title, so I just decided to call it comparing linear and exponential functions. In this first video, we're going to focus on the following problem. The population of a town grew from 27,300 in 2010 to 28,100 in 2011. We want to model the population of this town into the future with two different functions. One, part A, a linear function, and part B, an exponential function. And then once we've done that modeling, we want to compare and contrast these functions and what they predict. All right, before we go ahead and try to write down formulas for these functions and look at their graphs and their values, it's good to think about what's going on here with the population in terms of what many people call absolute change, or I prefer calling actual change, and relative change. What is the absolute or actual change, I'll call it actual, in the population from one year to the next year? It's just the difference. The population in 2011 minus the population in 2010, and that is 800 people. That's the actual change in the population. What's the relative change? That would be the percentage change. You take the actual change, which was the 800, and divide by the starting value, the value in the first year that we have in 2010. I'll just call it starting value. So 800 divided by 27,300, and if you've got your calculator, go ahead and do that. I'll do it here too. 800 divided by 27,300. About 2.93%. I'll go ahead and round it right now. 0.0293. 2.93% was the relative growth, the growth as a percentage from 2010 to 2011. All right, what a linear function does to model this growth is it takes the actual change and uses that, in a sense, as a basis for the formula for your function, whereas an exponential function takes the relative change, in a sense, as a basis for the formula for your function. What do I mean by those things? Well, hopefully you recall that a linear function has a slope, which can also be thought of as what's called a rate of change. Before I write down the formula for this, we probably should define our variables. Think about this. You're modeling a population as a function of something. What's it a function of? It's a function of the year, or if you prefer, of time. And it's probably best to think of the starting year, 2010, as time 0. But anyway, it probably would be good to use suggestive letters like P for population and T for time. I'm going to write delta P divided by delta T here. It's common, this triangle shape here is a capital Greek letter delta. It's common to use that letter as to mean changing, shorthand for change in P, change in T. These are two individual quantities, delta P and delta T, that give us the rate of change, the slope of this function, rise over run. Why is that? Well, if you draw a picture, I'll just draw a picture quick here. At time 0, the population was 27,300. At time 1, and this graph is not scaled in such a way that this point is the origin. It's not. Just realize that. At time 1, you're up to 28,100. The graph of a linear function is straight. That's why we call it linear. It's a line. And the rise is given by the change in P. 28,100 minus 27,300. In other words, the actual change in the population, in this case because it's over 1 year. I'll go ahead and write it as a difference again. Change in time is 1 minus 0. I picked 2011 as the next year just to keep it 1 year, but I could have picked something different, and I would want to use, if it was 2012, I'd want to go 2 minus 0. Time equals 0 is corresponding to 2010. Time equals 1 is corresponding to 2011. I could have also done 2011 minus 2010 here. Anyway, this is coming out to 800, but the units here are not people, it's people per year. People per year, because it's a ratio where the units on the top are people and the units on the bottom are years. Anyway, that's going to be the slope of your linear function. I'm going to call this function capital L for linear. Hopefully you recall that you take the slope times the independent variable. Oops, and this is the dependent variable, is supposed to be p. The slope times the independent variable. M is often what the slope is called. I'll go ahead and call it M. Times t, the independent variable, and then you add on your vertical axis intercept, p-intercept in this case, and it's always in this situation, it's the value of p when t is 0. It's the starting value of p in this case. I'll write it as a b here initially, but the formula is going to end up being 800 times t, and I'm not going to bother putting the dot there. I didn't have to put the dot there either. If I just put mt, it's understood that it's m times t. This is 800 times t plus 27,300. It's a linear function. I'm calling it L of t for linear. Its graph looks like this, and you can extend it into the future, and we will. Probably not in this video since we're getting close to 10 minutes here, but in a future video. Let's end this one by seeing if we can quickly write down an exponential function. That's also going to be an alternative model for this population growth. Again, I said you focus on the relative change with an exponential model. I'll call the exponential model capital E of t for exponential. Oops, sorry about that. There we go. And the form that exponential models take is the starting value of p in this case. I'll call it p sub 0. The subscript is just telling me it's the value of p at time 0. It is this quantity. This symbol represents just one quantity, the starting value, times. Well, one common way of writing what I'm about to write is like this: 1 plus r to the t. Notice the independent variable is now in a power instead of being multiplied by something. That's what makes this an exponential function, where r is really the rate of growth as a percentage without the percent sign, and where you put the decimal, where you take your percent version and move the decimal back to the left 2 places. In other words, based on what we did with our previous calculations, the p0 is the starting value, that's 27,300, and the r, if you recall, is 2.93%. I'll go ahead and show that to you again. 2.93%, but you want to write it in there as 0.0293 without the percent sign. 1 plus 0.0293 to the t. Go ahead and take 1 plus 0.0293. That'll be 1.0293. You could put parentheses here if you want to really emphasize to yourself that it's that number being raised to the t power. It is conventional to not bother with the parentheses sometimes, though if you don't put the parentheses, you'd want to put a dot here for times. And the order of operations here is very important. Exponentiation gets done before multiplication, so you would want to take 1.0293 and raise it to the t power before you multiply by 27,300, and that's also what the parentheses emphasize. Some people sometimes make the mistake of thinking both they need to multiply first and then raise to the t power, but that is not what you should do. Raise to the t power first, then multiply by 27,300. So in the next video, we will look at these functions more carefully, look at the graph of this one, and compare and contrast them.